Lesson 8.3, Solving Logarithmic and Exponential Equations, Part 1. So in this lesson, we're going to look at solving equations involving logarithms and exponentials. This lesson will focus on solving logarithmic equations, and the next one will focus on exponential equations. Now, before we get too far, let's remind ourselves of the idea of solving. Now, the entire first half of this unit on logs and exponential functions has focused mainly on evaluating. When it comes to algebra, there's really only three questions: evaluate, solve, and then everything else. You're either evaluating, you're solving, or you're doing some special case of a situation. Evaluating is when you plug something in and figure out what the output is. Solving is when the output is known and you're trying to figure out what the input was. So here we're solving because, for instance, on that first question, the output is 10. I want to know what x, the input, would have been to produce an output of 10. But then when it comes to solving, there's different types of solving. Here, clearly, we're going to solve by isolation, but there's also solving by factoring. Remember that the idea of factoring versus isolating comes down to the number of variables that you see. I see one variable on this equation, so I know I'm isolating. If I had multiple variables, I would attempt factoring. Now, when I'm solving by isolation, I'm going to be using the order of operations, but in reverse order. So I start with addition, subtraction, strip that away, and then multiplication, division, strip that away, and then any exponents, strip that away, and then anything left will work from there. So the idea is start from the outside of the function and work your way in. So with this function, we're going to start by stripping away the plus 2. So the inverse of plus 2 would be minus 2, so we'll do that on both sides. We're left with 4 fifth root of x equal to 8. Our next outer layer would be the multiplication of 4. The inverse of multiplication is division, so I'll divide both sides by 4. I get the fifth root of x equals 2. The next thing I need to strip away is that fifth root. The inverse of a root is an exponent, so the inverse of the fifth root would be the fifth power. So raise both sides to the fifth power, I get x equals 32. I could always take that 32, plug it back into the original question, 4 times the fifth root of 32 plus 2, and test it to make sure I get 10. Because it works, I know it's the correct answer. Looking at this second problem, pay attention to the parentheses. Because of the parentheses, I'm not going to start with getting rid of the plus 1. I'm going to start with the outer operation. In this case, it's not the plus 1 that's the outermost operation, it's the times 5. So I'll divide both sides by 5. I get sine of x plus 1 equals 1/5. The next outermost operation is sine, so I'll undo the sine using the inverse of sine, which is called inverse sine. I will take the inverse sine of both sides. That cancels out the sign on the left. We're left with x plus 1 equals the inverse sine of 1/5, and then I get rid of the plus 1 by subtracting 1 from both sides. Note that I'm not subtracting 1 from 1/5, I'm subtracting 1 from the right side. I'm subtracting 1 from inverse sine of 1/5. The inverse sine of 1/5 minus 1 is the inverse sine of 1/5 minus 1. So that's all we need to focus on in this lesson. Solving an equation by isolation just means using the inverse operations, using the reverse order of operations. Strip away the outer layer, one layer at a time, using the appropriate inverse operation. So here we need to focus on what's the inverse of the given operation. Well, keep in mind, a logarithm is the inverse of an exponential. A logarithm is the inverse of an exponential. I could say that the other way around as well, then an exponential is the inverse of a logarithm, which means a log cancels an exponential cancels a logarithm. Keep in mind that an exponential is not an exponent. X squared is not an exponential. 2 to the x is an exponential. I'm not talking about this guy right now. To get rid of a square, I'll use a square root. But if I have 2 to the x and I take a square root, that doesn't do anything. On the x squared, I'm left with x. On the square root of 2 to the x, I'm left with, really, it would be 2 to the x over 2. That doesn't do anything to the function that was there. It just makes it more complicated. To get rid of an exponential, I'm going to use a logarithm. So here's how it would look. Looking at the problem on the left, log base 2 of 2 to the x. because a logarithm cancels out an exponential, the only other thing we need to worry about is the index of the logarithm. The base has to match. Just like if I have x squared, I'm going to use a square root. If I have x cubed, I'm not going to use a square root, I'm going to use a cube root. If I have a +1, I'm not going to use a -7, I'm going to use a -1. I'm going to use the inverse operation with the same index value. So the inverse of an exponential is a logarithm. So if I have 2 to the x and I want to get rid of the 2, I'm not going to use a square root, I'm going to use a logarithm with a base of 2, because then the logarithm cancels with the base and I'm left with x. That statement could also be done a slightly different way. Recognize log properties allows me to bring the x to the front, and then I have x times log base 2 of 2. And of course log base 2 of 2 is 1, and 1 times x is x. But in general, we just say log base 2 of 2 cancels the 2 and it leaves the x. Same thing over here, 2 raised to the log base 2 of x. Log base 2 of x is asking what exponent would 2 need to be raised to get x. Well, that exponent, if I raise 2 to that exponent, I will get x. As long as they have the same index value, log base 2 and base 2 of the logarithm, they cancel each other out, and I'm just left with x. A logarithm cancels an exponential cancels a logarithm. So let's look at an example. Here is what a logarithmic equation would look like. It's just an equation involving a logarithm. The unknown is the input value, log base 3 of x equals 2. Now I could always eyeball this and just ask myself, okay, what number could I fill into this blank to make this statement true? Recall that a logarithm is asking 3 to what power gives me x. Well, if that power is 2, 3 to the second power gives me x, then x would have to be 3 squared, or 9. So I could always just eyeball it, and if I can recognize the answer, write it down and move on. But when I'm not able to eyeball it, I need a process. So in this case, I'm going to use isolation. The outermost operation is log base 3. I need to get rid of that log base 3. The inverse of a logarithm is an exponential, so I'll use an exponential of base 3. So what I'm going to do is I'm going to rewrite both sides, the left and the right side, as an exponential expression. Notice I did not multiply both sides by 3. I did not divide both sides by 3. I did not cube both sides. I exponentiated with a base of 3. I rewrote both sides as an exponential expression with a base of 3. The 3 needs to be down and to the left of what was originally there. The exponent needs to be up and to the right of the 3. I see people doing this all the time. They'll write a 3 here and then they'll write a 3 there. That 3 right there makes absolutely no sense. The 3 should be right here. So then canceling on the left, 3 and the log base 3 are gone. You're left with x equals 3 squared or x equals 9. Congratulations, we have just solved a logarithmic equation. Let's look at one that's slightly more complicated. Take a moment, pause here, try this on your own, play when you're ready. Alright, so we're going to solve by isolation, again because it says isolation at the top and because there's only one variable in this problem. Isolation means start on the outside, work your way in using inverse operations. So we'll start with that plus 2, we'll subtract 2 on both sides. We're left with 4 log base 5 of x minus 1 equals 8. The next operation to get rid of is the multiplication by 4, so we'll divide both sides by 4. We get log base 5 of x minus 1 equals 2. Alright, now here's the main event of this lesson. Let's get rid of that logarithm. The inverse of a logarithm is an exponential. The base of that exponential would need to be 5, so I will exponentiate base 5 on both sides. That cancels out the logarithm on the left. We're left with x minus 1 equals 5 squared on the right, which is 25. Finish it up by adding 1, we get 26. Final answer. Now, of course, anytime we're solving, we should always be able to check our answer when we're done. We could take that 26 and plug it back in at the top. And we could check this by hand. What's 26 minus 1? Well, that's 25. Log base 5 of 25 is going to be 2. 2 times 4 is 8. 8 plus 2 is 10. So I know x equals 26 is correct. I can also use my calculator to check my answer. The thing about it, though, is I told you in a previous lesson that I can only use my calculator to evaluate log base 10 and log base e. Now, of course, I could use the change of base formula and rewrite this in my calculator as log base So it would end up being 26 minus 1, so this would be 4 times log base of 25 over log 5. I could type that in my calculator and check my answer using the calculator. But also, I lied earlier when I said that you can't do a logarithm other than the common log and the natural log in your calculator. If you have the newer TI-84s, the older TI-84s or the TI-83, you're not going to be able to do this. I have no idea if you can do this on other branded calculators, but if you have the TI-84 with the updated operating system, just hit alpha and then F2, and you'll see a menu pop up with a bunch of functions that may or may not appear anywhere else on this calculator. Look at option 5, that's log of any base. So you could actually type this into your calculator once you get x equals 26. Just type it in your calculator exactly as you see it. Instead of having to use the change of base to type this in, we could just type it in as 4 log base 5 of 26 minus 1 plus 2. Check our answer. Yep, we sure do. We get 10. I always like to wait until this moment to tell you about that operation on your calculator because I want to force you to practice using that change of base formula earlier on. All right, here's another question. Pause here, play when you're ready. All right, so we'll start by getting rid of the outermost operation. I see that 1 on the outside, so I'll subtract 1 on both sides. We get negative 11. Then I'll divide both sides by negative 5. We get 11 fifths. I especially like this question because of what's happening on the right side. Ooh, that's looking ugly on the right side. I don't care about the right side. When you are solving by isolation, you should be able to completely ignore the right side, let whatever happens to the right side happens to the right side. Your only focus is on the left side of the equation. Use inverse operations, getting rid of one layer at a time. Whatever happens to the right side, don't worry about it, just let it happen. So on the left side I subtracted 1, then I divided by negative 5. My next step is to exponentiate with a base of 4, which is going to allow me to cancel out that logarithm right there. I'm left with x minus 2 equals 4 to the 11 fifths. Add 2 on both sides. Now keep in mind when I add 2 on both sides, I am not adding 2 to the 4 directly, I am adding 2 to the entire right side. So 4 to the 11 fifths plus 2 is 4 to the 11 fifths plus 2. I can't add 4 and 2 before I perform the exponent 4 to the 11 fifths. Since I don't know what 4 to the 11 fifths is, I'm just going to write 4 to the 11 fifths plus 2. Also, if you want to rewrite that as the 5th root of 4 to the 11th, you go right ahead. My issue with doing that is the second part of this question. I need to approximate my solution because that, as soon as x is by itself, I'm done. That is my exact answer. X equals 4 to the 11 fifths plus 2. To approximate it, I'm going to type this into a calculator, and rewriting 4 to the 11 fifths as a 5th root makes the calculator a little bit more challenging because, again, I don't know where the 5th root button is on my calculator. Of course, that's a lie. I know where it is, but I'm going to guess that you don't, and I have no interest in telling you where it is. So just write it as 4 to the 11 fifths plus 2. I get 23.112. And just like we did before, we can check that answer in the calculator just to make sure. Notice here's me retyping the given expression 1 minus 5 log base 4 of x minus 2, but instead of writing x, I wrote answer. Keep in mind you can find the answer button. That's actually the negative key on your calculator, so if you just hit second negative, that'll pull whatever the previous answer was, minus 2, and look at that, I get negative 10, which is exactly the output I predicted. Therefore, I know this is the correct answer. Here are 3 more for you to try on your own. Pause here, play when you're ready. Remember, I need both exact and approximate solutions where applicable. So here we're going to subtract 5, divide by 3, and then remember ln actually means log base e. All right. I see people writing ln base e a lot. Please don't do that. It's ln or log base e. There's no such thing as ln base e. So ln is log base e, so if I exponentiate both sides with the common base of e, that's going to cancel out the ln on the left side, and we're left with x equals e to the first, or just e, which I hope you're not grabbing a calculator for e, because I told you to memorize e as 2.718. Final answer. Next one, log of x squared equals 4. Now on this one, there's a couple different routes to get the answer here, but one of those routes is incredibly dangerous. Now, if you do this the way I intend you to do this, then you recognize log of x squared actually has invisible parentheses, log, and then inside the parentheses is x squared, which if we're following the rules of isolation, we're going to get rid of the logarithm before we get rid of the square. So getting rid of the logarithm, that's a common log, so we'll use base 10. That leaves me with x squared equals 10 to the 4th, or 10,000. And then we'll take a square root of both sides, and then here is the next place where we often make our mistake. I still don't understand why people still make this mistake in high school, but a square root, every time you take a square root, plus or minus. There are two answers to this question. X equals positive 100 and x equals negative 100. Now, alternatively, some of you I know looked at this problem and thought to yourself, wait a second, I can bring that 2 to the front. And you are absolutely correct. You can bring that 2 to the front. And then if I solve by isolation, divide both sides by 2, exponentiate base 10 on both sides, I get x equals 10 squared, which is 100. But the problem is the correct answer is both positive and negative 100, not just positive 100. Now, of course, if you know that the correct answer is supposed to be plus or minus, then maybe you take this answer over here and just slap a plus or minus in front of it in order to get the right answer. But that's not how math works. You don't know what the answer is before you find what the answer is. And you definitely don't just throw in a plus or minus because you decided to put in a plus or minus. On the example on the left there, we put in the plus or minus because of the specific rule about square roots. We justifiably put the plus or minus because we took a square root. In this problem over here, there would be no justifiable reason to put a plus or a minus, which means this is incorrect. You cannot solve this equation using that technique. The problem has to do with that square. When there's a square, that means there's two answers. But over here, by bringing that square to the front, this is now first degree, which means there's only one answer. By using that power rule to bring the 2 to the front, you have changed the degree of the equation, and thus you have changed the number of solutions of the equation. Do not take actions that changes the intended outcome of the problem. Because bringing that 2 to the front would change the number of solutions, I don't want to apply that property. So in this case, you want to leave that square where it is and just isolate from outside in. Plus or minus 100 is my exact answer. Now, on this one, there is no approximate solution because 100 cannot be approximated. Approximating is converting to a decimal and then either truncating or rounding off that decimal. If you have a whole number, you can't approximate it. So, final answer. Take a look at this one. Pause here. Play when you're ready. All right, so we're going to start by getting rid of the 3 out front, and then keep in mind you can't exponentiate the logarithm until you get rid of that negative, so we'll divide both sides by a negative, and we get log base 4 of the square root of x minus 8 equals positive 3. Exponentiate both sides, you're going to get square root of x minus 8 equals 4 cubed. Now 4 cubed, of course, that's 64, but again, I don't care what happens on the right side of this equation. My goal is to solve. The goal is to get x by itself. If you want to rewrite 4 cubed as 64, you go right ahead. I don't care. My next step is to get rid of the square root, so I'll square both sides. Now, when I square the 4 cubed squared, power to a power is a product, that's just going to be 4 to the 6th. Or you could have 64 squared. Or you could have what I think it comes out to 4096. I don't care what you have on the right side of the equation. As long as it's accurate, I don't care. The goal is to get x by itself, so I'll add 8. So there's my exact answer. Now, again, for approximation purposes, if you were to rewrite this as, so that would be 4096 plus 8, which would be 4104. That's an exact answer. That's not an approximation. There is no approximation for this one. I'm done. Now let's look at a fun one. ln of x minus ln of 2 equals 7. Now, I'm going to start the same way I expect you to start this problem. I've been teaching this for long enough to know exactly what you're going to do when you look at this problem, although I'm sure some of you are going to do this perfect from the first attempt. Others are going to do what I'm about to do right here. I see ln of x minus ln of 2 equals 7. I want to get that x by itself, so let's start by exponentiating. Would be base e on both sides. Now, since I see multiple terms, I'll go ahead and do it term by term. All right. So then the exponential would cancel out the logarithm, exponential would cancel out the logarithm, we're left with x minus 2 equals e to the 7th. Add 2, e to the 7th plus 2 is my answer, which is not correct. That is not the correct answer. Nothing I did here, well, I guess one thing I did here was correct. I added 2 to both sides. That was correct. Everything else was wrong. Consider e to the 7th plus 2, this is my decimal approximation, and if I check that in the original question, I do not get 7. I'm supposed to get 7, but I do not get 7, which means e to the 7th plus 2 is not the correct answer. Now, of course, my mistake here was completely ignoring how to solve an equation. Isolation means you strip away the outer layer first, and you go one layer at a time. Here, I just randomly decided to start with getting rid of the ln. That's not correct. I can't do things out of order. Now, also, the way I exponentiated was false. That is not true. Consider the completely true statement that 1 plus 2 equals 3. Hopefully you agree with me that 1 plus 2 equals 3. Now, if I do the same thing I did up here with the exponential, the exponentiating each term individually, so pick a random number, how about 4? If I do the same thing I did up here, exponentiating one term at a time, but with a base of 4, 4 to the first, 4 to the second, 4 to the third, and take a look, 4 to the first is 4, 4 to the second is 16, 4 to the third is 64. 4 plus 16 is not equal to 64. Thus, it is illegal to exponentiate one term at a time. You cannot perform operations one term at a time, because essentially what I'm doing there is I'm distributing the operation. And as I've said in this course 487 million times, you cannot distribute an operation. Do not distribute an operation. You do not do this one term at a time, you do it one side at a time. What I could have done is exponentiated the base 4 on both sides. So that's not 4 to the first and 4 to the second separately. It's 4 to the left side, so 4 to the 1 plus 2, and 4 to the right side, 4 to the third. 1 plus 2 is of course 3, so that is absolutely a true statement right here. Now if I bring that up here and exponentiate, again base e because I have ln, exponentiate both sides separately, not e to each term, but e to the left side completely, then it's e raised to the ln of x minus ln of 2 equals e to the 7th. That is perfectly legal right there. But the problem is I'm stuck. My goal is to strip things away from the x, not add things onto the x. By exponentiating the left side, I've kind of got a dead end here. I can't exponentiate each term at a time. Again, it's illegal to distribute an exponent. So there's really nowhere to go from here. This one is legal, but not useful. So let's go back to the original question, and let's actually follow the rules this time. Let's get x by itself. What's x hanging out with? Well, it's hanging out with the ln, but it's also hanging out with the subtraction of the ln of 2. So what should I be getting rid of first? Not the ln in front of the x, but the ln of 2. Start by adding ln of 2 to both sides, and then, again, I don't care about the right side. Don't look at the right side at all. Just let whatever happens to the right side happen to the right side. Now let's focus on this statement right here. How do I get x by itself? Well, the only operation left is ln, so now is the correct time to exponentiate both sides. I don't exponentiate and then add. I add and then exponentiate. So the e and the ln cancel out. I'm left with e raised to the 7 plus ln of 2. Typing that into a calculator, I get this number. Checking that again with the calculator, plug it into the original function, I get the correct output. Follow the order of operations in the correct order, and you will get the correct answer. But I'm not done. This question, although this technique works perfectly well, there was another way to deal with it. Now, I'm still focusing on that subtraction first. The goal is to get rid of the subtraction. One way to get rid of the subtraction is by adding the ln to the other side. But because this is a logarithm, another way to get rid of the subtraction is using a log property. Instead of adding the ln of 2 to the other side, I could have condensed this using the quotient rule into ln of x over 2 equals 7. Now, continue with my isolation properties. Get rid of the ln would be my next step, so exponentiate base e on both sides. That's going to leave me with x over 2 equals e to the 7th. And then get rid of division by 2 by multiplying both sides by 2, and I get my answer of 2e to the 7th, which when I type that in the calculator, you're going to see it comes out to be exactly the same answer I got before. Now, as I keep saying, logarithms and exponent properties, there's multiple ways of getting right answers here. Through practice, you build an intuition, and through your intuition, you develop which techniques you prefer versus other techniques. I don't care which technique you use. As long as you get the right answer, I'm perfectly happy. Out of these two options, I prefer this one, and it's always nice to know which technique your teacher is going to use. All right, here's another one. Pause here, play when you're ready. So, just like before, I could start by subtracting log base 3 of 2 on both sides to get the x by itself, and then get rid of the other log base 3 and then get rid of the 5. That would absolutely work, but I'm not going to do it that way. I'm going to start by using a log property. Addition becomes multiplication. 5 plus x gets multiplied by 2. If I distribute, that would become 10 plus 2x. Exponentiate both sides with a base of 3. That gets rid of the logarithm on the left and gives me 3 squared, or 9 on the right. Subtract 10, divide by 2. X equals negative 1/2. Keep in mind, if I attempt to convert negative 1/2 to decimal to get my approximate solution, I get negative 0.5. That is not an approximation. That is also an exact answer. So this one does not have an approximate solution. Here are two more. Pause here, play when you're ready. All right, again, I'm going to stick to using log properties to solve these. First one first. Addition becomes multiplication, so that's 6x. Exponentiate both sides. Base e is going to give me 6x equals e squared. X equals e squared over 6, or 1.231. And the last one, subtraction becomes division. Base 10 on both sides is going to give me 10 squared, or 100 on the right side. Now, when it comes to solving fractions with the variable and denominator, I'm going to remember, hey, wait a second, that's really over 1, and there's a property of proportions that allows me to switch the corners on a proportion. So 6 over 100 equals x plus 3 over 1. Subtract 3, and that technically is my final answer. If you want to clean that up, that would be 3 over 50, which becomes 3 over 50 minus 150 over 50, which is really negative 147 over 50, which, if you convert to decimal, comes out to a terminating decimal. I believe it was negative 0. I've completely forgotten. Whatever it is, I know it comes out to a terminating decimal, so that is not approximatable. So I'm just going to box this as my final answer.